question number 3. An electron moves in a circular orbit in a uniform magnetic field. Okay, so this is an electron which is moving in a uniform magnetic field direction is not shown. Okay, so velocity vector is shown. The velocity of the electron at point B is 6.8 into 10 power 5 meters per second. This B is given to you, the direction shown. The magnitude of the magnetic field is 8.5 Tesla. Okay, so magnitude is also given to you. State the direction of the magnetic field. So how do you find the direction? So what do we do? First, what you do is, whenever there is a negative charge being given, assume it is positive charge. Find out the rule, use the rule to find out what is the direction of the magnetic field. And later on, what you do is, you find out what will happen with the magnetic field if the charge is flipped. Okay, so therefore, now if this was a positive charge, then what will you do? See, first FBI is your left hand rule we are using. Okay, so therefore, so current is nothing but the direction of the positive charge. I is the direction of the positive charge. Current is moving like this over here. Okay, and then B. What is B? B do I do not know. What is the magnetic field? Now force. What is the force? See, when an electron is moving in a circular path, we know that the force is always directed towards the center, right? So it's been directed towards the center here. What do you call this forces? Centripetal force, right? So here also it is directed like this. Here also it is directed like this. Here also it is directed like this. It's always directed. Now what we do is, I keep my fingers like this, and I keep on turning like this. If I keep on turning like this, what will happen? The velocity vector here is in this way. The force is like this over here. If it is like this, the force is like this over here. See, this agrees very well with the diagram that I have written. What does it tell you? That means if the charge was positive, the force is in this direction. The force is in this direction. Okay, the force is right. The force is correct. Charge velocity is also correct direction. If it was positive, and then the magnetic field will be directed inwards, right? The magnetic field was directed inwards. But since the charge is negative, for getting the same effect as that of the force, now what should be the magnetic field direction? This finger should be flipped over, right? It should be flipped over here. Force should not change, because now this is going to change. I will not be able to show it over here, okay, because I cannot twist my finger like this over here. So what I do is, I consider if this finger is like this, this remains the same. This would be like this, right? So which means it's towards me. In other words, the magnetic field is like this. So what should I write? I should write to state the direction of the magnetic field. It is away from the page. You can write away from the page, or maybe you can also write it's out of the plane. Okay, so either of them, I think out of the plane would be a better one to write it. Okay, let us move on to the next one. So calculate in Newton the magnitude of the magnetic force acting on the electron. We need to find out what? Magnetic force. So this is given by the formula F is equal to QVB sin theta. Now let us see whether all these values are known to us. What is being given? Q. What is Q here? Electron. So the electron value is known. The charge on an electron is 1.6 into 10 power minus 19. What is the velocity of the electron? Is it given? Velocity of the electron is given as 6.8 into 10 power 5 is also given. 6.8 10 to the power of 5. What is the value of B? 8.5 Tesla. 8.5. What is the theta value here? 90 degrees. What is theta? The angle between the force and the velocity vector. See, force is like this, velocity is like this. Angle between them is 90. So sin 90 becomes 1 over here. So let us compute these values and get the final answer. So this would now become 1.6 multiplied by 6.8 multiplied by 8.5 will become 92.48. So this becomes 92.48 into 10 to the power of minus 19 plus 5 would be 10 power minus 14, which in turn can be written as 9.2 into 10 to the power of minus 30 Newton, right? So this should be the right answer. Let us move on to the next. It's not working. Okay. Explain why the electron moves at a constant speed. What is the? Why does the electron move at a constant speed? The reason is, see. So first of all, why should electron move? Because there is a force at it. Now what does the force do? Force should do some work here, right? Now what does the magnetic force do? This is the general thing which we have. Okay. Whenever you have a force, the force applied will make the object to move across. And thereby what can happen? If it is acting in the same direction, the speed of the object will increase. If it is opposite in the opposite direction, the moving object will slow down. This is what can happen. But there is one more chance also. What is that? Okay, so it can change the direction of the object. So therefore here what's happening? So here the magnetic force does not change the kinetic energy of the electron. Which means what? If you say kinetic energy is not changed, neither the mass is changing. Mass will never change. Okay, the velocity is also not changing. Which means the speed will remain a constant. Now, if you ask me why the magnetic force does not change the kinetic energy of the electron, you can always give one more reason. You can say the magnetic force P, okay, and velocity, they are perpendicular to each other, and as a result of it, work done will be equal to 0, right? When force is perpendicular to distance, there is no work done by the force, right? For example, you have an object, so you would have studied this in mechanics. You have an object of mass m over here. If this object is moving like this, okay, and what you do is you apply a force over here like this, or maybe you can say what is the work done by the gravity, making the object move like this over here. You can definitely say there is no work done by the gravity when the object is moving in the horizontal direction. Let's say the frictionless plane and the object is moving with an uniform velocity. Okay, this force will not have any effect on this, right? So only when the force is aiding like this or opposing like this, or making an angle like this over here, okay, or maybe making an angle like this over here. Anyway, but the angle between the force and the velocity vector should not be 90. Only then work done is not equal to 0. Okay, if the angle between them is equal to 90, then work done is equal to 0. Because mathematically also, because this is logically we have shown, okay, mathematically also you can say that f dot v, what does f dot v tell you? Power multiplied by time is nothing but your work done, right? So therefore f dot v, a dot b is equal to 0 if the angle between a and b are 0. So as a result of it, this definitely is not possible. You can also say its power, you can also say f dot s is also equal to 0, because you know S is a displacement here, F is a work done. Okay, so you can also define work done as F dot S. This is the actual way how you define the work load. Okay, now let us look at the next problem. Next part of the problem tells you why does it move on to a circular path? Why doesn't the electron move in the circular path? See, what is the condition for a circular path? The condition for a circular path is that whenever the force is perpendicular to velocity, particle moves in a circular path. This is the only condition, okay, for the particle to move in a circular path. For example, if a particle is moving in a circle, what will happen here? There is a force acting like this over here, and there is a velocity vector like this. At every point, this is the same thing. We would have studied this in case of your tension, okay, in case of variable forces. Okay, when you have a circular motion, what did we have? Okay, you have an object and you used to spin it across, and that happens only when the force and the displacement vector, the velocity vector, are perpendicular to each other. So in this case also, these two are perpendicular to each other, and as a result of it, the path of an electron in a magnetic field will always be circular in nature. Okay, so with this, I think we have come to an end to this question. See you tomorrow with the next question. Thank you.